Hello everyone and welcome back. Now we're going to be digging a little bit deeper into the whole idea of Taylor series, and what we'll learn about is the error that we get when we use a Taylor polynomial of degree n to approximate a function f of x. So in other words, as this indicates, a function will be approximately equal to a Taylor polynomial of degree n right here. And really what we're looking for is, what is the error when we approximate f of x with a Taylor polynomial of degree n? And the error is basically the absolute value of the difference between those two expressions. So as an example, let's suppose we have some function x, f of x, and we're expressing it as a Maclaurin series. Now, note that this piece right here is what we call p sub 2 of x. This is a Taylor polynomial of degree 2, quadratic function. So what we're saying is that f of x can be approximated by p sub 2 of x. And the error, well actually let's give it the true name. The truncation error is just everything else, which is a sub 3 x cubed plus a sub 4 x to the fourth, and so on. It's all of the essentially unused terms that we just discarded or truncated. So let's check this out a little bit with an example. So this actually is a simple example to begin with. We'll talk about a function f of x being 1 over 1 minus x. We're accustomed to this. And here is the power series, or now as we call it, the Maclaurin series. And we know that we only have equality here when the absolute value of x is less than 1. X is the common ratio, and that has to be less than 1. So here's the deal. We're going to use p sub 3 of 1/2 to approximate f of 1/2. And let's talk about what the error should be there. So it's important to note that this is a special case, and it does make things a lot easier. As we have already discussed, this is a geometric series, and it has a lot of special properties that we'll bring to bear on the solution. First of all, let's note that f of 1/2, in other words, what we get when we put 1/2 in here, is just equal to 2. So it's very easy to compute what f of 1/2 is. Now, p sub 3 of 1/2 is simply the cubic part of the Maclaurin series evaluated at 1/2. And so it's 1 plus a half squared plus a half cubed. That's it. And we can see that this is equal to 15 over 8. Pretty close to 2. Clearly, if we used more terms, if instead of 3 we were 4 or 5 or 6, this would become a better approximation. But now let's talk about the error. So the error is simply everything else. And so we get as the error, it's going to be 1/2 to the fourth plus 1/2 to the fifth, and so on. Now this is a geometric series. And so it equals the first term, which is 1/2 to the fourth, divided by 1 minus the ratio, which is a half. And if we compute this carefully enough, it turns out to equal 1/8. And because this is a geometric series, and we can do this exactly, 1/8 is precisely how much 15/8 differs from the exact value of 2. So this should help you understand how you can find an error just in the case of a geometric series, which is really pretty simple. Okay, so now let's put down what Taylor's theorem says, and Taylor's theorem is what gives us that first handle on how to compute an error in general. Okay, so here is what Taylor's theorem says. We begin with the natural assumption that f has derivatives of all orders and some open interval I about x equals a, and a is going to be the center of this Taylor series. Then what it says is for any positive integer and for any x in this interval, well, here's f of x as a Taylor series. So we stop right here, and this is p sub n of x, and then it's saying, okay, plus something else. And that's kind of the remainder, and that's the everything else, that's the truncated error. And what Taylor's theorem says is that this truncated error of degree n is equal to this expression. And the big deal here is this term right here. Everything else is pretty easy to figure out, but this represents the n plus first derivative at c for some c between a and x. And it turns out to be that c which makes this be as big as possible. So just to repeat this very important idea, r sub n of x, that remainder term, is the error that we get if we approximate f of x with p sub n of x, which is the nth degree Taylor polynomial. And so it should be pretty clear that f of x will indeed converge to this Taylor series if and only if the limit of this expression, the error expression, goes to 0 as n gets very, very large. So, to kind of bring this to a conclusion, what we have is the remainder estimation theorem, which tells us that the remainder, absolute value of the remainder, or the error, let's make sure that that's clear, the error in approximating f of x with p sub n of x will always be less than or equal to some number m times x minus a to the n plus 1 over n plus 1 factorial. X is the value we're approximating, a is the center. Now, this is the hard part. M is the upper bound of the n plus first derivative of the function for any t between a and x. So in other words, it's the biggest value that the n plus first derivative assumes for all values between the center and whatever value we're approximating. This value may be bigger than a or less than a. And that is the big deal, and that is how we find the error. Okay, so here's a realistic example. Let's suppose we have a function f of x equaling the square root of 1 plus x. And we're going to use a second degree Taylor polynomial at 1 to approximate f of 1. And f of 1 is simply the square root of 2. So I think we'll conclude all the ugly work for this problem, and I'll write it out right now. So you should be able to figure out all of this work, taking a bunch of derivatives, evaluating them at 0, and then finding the coefficients. And so what this tells us is that p sub 2 of x is equal to 1 plus 1/2 x minus 1/8 x squared. And so therefore, p sub 2 of 1 will equal 11 over 8. All right, so now we want to find the error. So the error is the actual value for f of 1, which is the square root of 2, minus the approximation, which we got with the second degree polynomial, and we found that to be 11/8. And so this error then is going to be less than or equal to some number m times 1 minus 0 cubed over 3 factorial. And m is the upper bound, or the maximum value, of the third derivative of x, which is 3/8 times 1 plus x to the minus 5/2 on the interval 0 to 1. And so since this is going to be in the bottom, to make it be as big as possible, we make that be as small as possible, and that will tell us that this value for m is just going to be 3/8. And so, let's just save us some room. If we go back up here, the error is going to equal 3/8 times 1 over 3 factorial, which is equal to 1/16. So therefore, that means that this difference is less than or equal to 1/16. And finally, what we can say then is that the square root of 2 has to be between 11/8 plus 1/16 and 11/8 minus 1/16, and this is equal to 23/16, and this is equal to 21/16. So therefore, whatever the square root of 2 is, has got to be somewhere between 21/16 and 23/16. So take some time and make sure you can figure out all the steps in this. So here's a slightly different type of problem. Let's suppose that we're given our old buddy 1 over 1 minus x. P sub 3 of x, the third degree Taylor polynomial, is right here. And here the question asks, find the error that we'll get if we use P sub 3 of x to approximate f of x anywhere in this interval. So we're looking for the maximum error. So this error will be less than or equal to m times 0.1 to the fourth over 4 factorial. And what is m? M is the upper bound, greatest value, of the absolute value of the fourth derivative of x on the interval minus 0.1 to 0.1. Okay? So the fourth degree, the absolute value of the fourth degree derivative of f of x is 24 over 1 minus x to the fifth. And what we want to do is get the biggest value for that over the interval minus 0.1 to 0.1. And we'll get that to be as big as possible by making this be as small as possible. And that will happen if we choose x equal to 0.1. And when we do that, m is going to turn out to equal 40.6442. And so therefore the error will be less than or equal to 40.6442 over 4 factorial times 0.1 to the fourth. And finally this error comes out to be 1.69 times 10 to the minus fourth. So what that tells us is that if we use P sub 3 of x to approximate f of x anywhere in the interval minus 0.1 to 0.1, then the biggest error that we'll ever get will be this. Okay, so I'd like to finish by showing you what is Euler's formula, which is one of the most coolest formulas that we get. In fact, there was a big contest held by mathematicians, and they came up with the statement that this is the best formula in all of mathematics, believe it or not. So let me just set up some Maclaurin series to begin with. Okay, so here are some Maclaurin series that you should be familiar with by now for e to the x, sine of x, and cos of x. And although it's a little bit beyond the scope of this course, what we're going to do is look at the expansion of e to the I theta, where I is the imaginary number, the square root of minus 1. And it should be believable to you, or if it's not believable, at least let me state it, that this formula up here works not only for real values of x, but also for imaginary values of x. So I'll write out what the expansion is for e to the I theta while you think about this. So all I've done here is to replace x with I theta. Now you're going to need to remember that when we expand this, that I squared is minus 1, that I cubed is minus I. Let me write it out. I squared is minus 1, I cubed is minus I, and I to the fourth is 1, and I to the fifth is I, and we're back repeating. So this is powers of I are cyclical in an order of 4. So I'll simplify this to make time a little bit easier. So do you see a pattern here? Think about the terms that just have I in them, and what do they remind you of? And think of the terms that don't have I in them, and think about what they remind you of, and look up to the top. So we'll go on and kind of group these together. So just to make it easier to follow, I've rewritten what e to the I theta is from the previous page, and now I'll do some grouping for you. So look what happens when we do some grouping. Does this look familiar to you now? How about this? Does that look familiar? You should be able to see now that e to the I theta is equal to cosine of theta plus I times the sine of theta. How cool is that? And that's sometimes abbreviated in mathematical shorthand as cis of theta for cosine I sine. So this is a very, very important result, and that is what is known as Euler's formula. And now for this really important, well, not important, just mind-boggling result, what we'll do now is, let's see what happens if we let theta equal pi. We get e to the pi I is equal to cosine of pi plus I times the sine of pi. And what that gives us is e to the pi I is equal to minus 1 plus 0. And so we finally get this result, that e to the I pi plus 1 is equal to 0. And that is what mathematicians have said is the top formula of all time. Notice what it does. It gets into what I call the big five. 0, 1, e, I, and pi. Gets into addition. It uses an equation. Gets into exponentiation. And it gets into multiplication. It is the most beautiful formula in all of mathematics. And there it is. Pretty cool. And you earned it. Okie dokie. See you next time.